So this talk will be a continuation of a talk that I gave here last year, but I won't assume that you were here or that you remember anything from that talk. So the talk last year was about the phase structure of QCD in 2+1 space-time dimensions, and in particular about how the conformal window ends there. And my talk today will be a more general talk about how what conformal windows are and how they can end. And I apologize that this year I will not be giving a Blackboard talk because I have too many graphs that I want to show you, but still please do feel free to stop me with questions at any time, even though this is not a Blackboard talk. So I'll begin by outlining the question of conformal windows motivated by the conformal windows of QCD in 3+1 and in 2+1 dimensions. I'll describe the general setup, and then I'll discuss what are all the possibilities for how conformal windows can end and how this can be identified. And the second part of my talk will be devoted to describing in detail 3 very specific examples where we can really control how conformal window ends and illustrate these different scenarios for how conformal windows can end. And I'll end with a summary and some future directions. And this talk is based on work that should hopefully appear very soon in collaboration with Thomas Dumitrescu, who's in the audience, and with my student, Jiangguan Xian. So the main motivation is understanding conformal windows like the ones that appear in QCD. So we're interested here in QCD, which is essentially the same Lagrangian as we have for the strong nuclear interactions in nature, except that we'll take the quarks to be massless to make things more interesting. And we'll analyze general values of the number of colors NC and the number of flavors NF. So we have this very simple Lagrangian describing the theory. And we have, since we'll use massless fermions, we have a chiral symmetry, SUNF cross SUN1, and also a baryon number symmetry. And then with these symmetries, this is really the most general renormalizable action. So it's a well-defined question to ask. What happens if we begin with this action, flow to low energies? What do we get at low energies? And of course, it's known for more than 50 years that this theory is asymptotically free if the number of colors is less than 11.5 times the number of flavors. So if NF is bigger than this, then the theory is just infrared free and doesn't do anything interesting at low energies. But below this bound, the coupling starts becoming larger as we go down in energy. And then if NF is only slightly smaller than 11.5 NC, so for instance, for SU3, if the number of flavors is 16, then the one-loop beta function is negative and very small, while the two-loop beta function is positive, so that they can cancel, and we have a non-trivial fixed point of the renormalization group at some gauge coupling G, which is G star. So in this regime of NF slightly smaller than 11.5 NC, we know from perturbation theory that the theory flows to a weakly coupled fixed point, which is some non-trivial conformal field theory. And then it's believed that as we decrease the number of flavors, this conformal theory becomes more and more strongly coupled, but it still continues to exist for some range in the number of flavors. However, if we then continue going down in the number of flavors, eventually there is a transition, and we go over to a phase similar to what we see in nature for SU3 with 3 late flavors, where we have confinement and chiral symmetry breaking. So there is this phase diagram where there is some range in the number of flavors where we flow to a conformal field theory, and another range where we have confinement and chiral symmetry breaking. And it would be nice to understand what is this critical number of flavors where we transition from one behavior to the other, and what this transition behaves like. Unfortunately, since this transition happens at strong coupling, we do not know how to compute analytically what is this critical number of flavors. It has been investigated in many lattice simulations, so I won't have space here to give credit to all the lattice studies of this question. And I think the consensus from the lattice papers is that for SU3, this transition happens somewhere between 8 and 10 flavors. So the main topic of this talk will be to ask what happens when we approach the end of this conformal window. How does it transition from a conformal theory to become a confining and chiral symmetry breaking theory in this case? Now, of course, for SU3, this is not a very sharp question because NF is an integer, so we have one value of NF where we flow to a CFT, then another value where we have confinement. But of course, this transition is not, I mean, it's a discrete parameter, so this is not a sharp question. However, we can make this into a sharp question by taking the large n limit. So we will take a large number of colors and also a large number of flavors while keeping the ratio x constant in the large unlimit. So in this limit, this parameter x becomes almost continuous. We still have inferred freedom when x is bigger than 11.5 and a weakly coupled CFT slightly below this range. And then eventually, we have this transition to Carroll symmetry breaking. Now, we have in the middle, we have this family of conformal theories. Of course, it's important to emphasize that these conformal theories along this line are not really continuously related to each other. For instance, they have different flavor symmetries. Each one has an SUNF cross SUNF flavor symmetry, which of course does very strongly when we move along this direction. But in the large unlimit, many properties of this conformal theory do behave continuously and smoothly as a function of x. For instance, the anomalous dimensions of various operators and correlation functions of light operators are believed to depend smoothly on this parameter x. So in this limit, we really do have a continuous parameter that labels this family of CFTs, and more generally, this family of renormalization group flows from the weakly coupled QCD at high energies to this low energy behavior. And it becomes a well-defined question to ask, what happens at this transition, at this critical value of x? How do we go over from this conformal field theory regime to the confining and Carroll symmetry breaking regime? So that question is the main motivation for this talk. So of course, we're particularly interested in this question for 3+1 dimensional QCD, but similar questions occur also in many other theories. For example, in 2+1 dimensional QCD, there's also a similar story. In that case, NF could be as large as we want, and if NF becomes very large, then again, we have a weakly coupled conformal theory that's controlled in this case not by perturbation theory, but by the expansion in a large number of flavors. So when NF is much bigger than NC, again, we have a weakly coupled conformal theory, while we know that for a small number of flavors, I guess 40 years ago, Buff and Witten proved that in this regime, we have Carroll symmetry breaking to UNF over 2 cross UNF over 2. So we have a very similar phase diagram to the one that we have in 3+1 dimensions. And again, in the large unlimit, we can ask what controls this transition from the conformal field theory regime to this regime where we have confinement and flavor symmetry breaking. In the 2+1 dimensional case, we can also add an extra discrete parameter by adding also a Chern-Simons coupling K for this SUNC gauge theory. And then we actually have 3 discrete parameters, K, NF, and NC. And it's interesting to analyze this theory in the limit where all 3 of these discrete parameters become large, but with some fixed ratios. So then this becomes a 2-dimensional phase diagram where in one region, we know that we flow to a conformal theory, which is weakly coupled if either K or NF becomes large. But when both of them are small, then we know that we have this other phase, and it's interesting to ask, how does this conformal window end? In this case, we can ask that when we approach this transition in various different directions. I should mention that if K is non-zero, then we have to fine-tune the Fermion mass because it's no longer protected by parity invariance, as it is without the Chern-Simons term. But we can still always fine-tune the Faraday mass to the fixed point, and then ask what happens when we do that fine-tuning and change these continuous parameters. We still expect to have some transition where the conformal window ends, and we'd like to understand what that transition behaves like. So the more general setup that I'll analyze in this talk is a family of renormalization group flows from some high-energy gauge theory to low energies, and we want to have some set of discrete parameters, which in the large NC limit may become continuous parameters that parameterize the flow. We'd like to have some region in this parameter space when we flow to a conformal fixed point, perhaps with some fine-tuning. And so in that region, we have what we call the conformal window, where we flow to a conformal fixed point. And we want to have some other region where we do not flow to a fixed point. And we want to ask, how does the transition between these 2 regions behave? So that will be the general question that I'll try to address in this talk. So. Exactly, yes. So in this large limit, it becomes a continuous parameter, and yes, so the analysis will indeed be very analogous to the study of phase transitions, and that's what I'll mention in my next slide. I should also mention that we discussed it here for Lorentz invariant theories, but there are similar issues that come up when we have renormalization group flows on boundaries or defects and so on, so there's an obvious generalization to that case. Now, these renormalization group flows may, in addition to the discrete parameters that I mentioned, they could also involve continuous parameters. And if the high energy theory has more than one relevant operators, then we have RG invariant ratios of these couplings. So we might have extra continuous parameters, and the behavior of the conformal window could also depend on the values of these continuous parameters. Now, in principle, we could also just fix the discrete parameter and ask what happens when we only vary the continuous parameters. And then, as Tim was implying, then this becomes exactly the usual question in phase transitions of what happens when you change continuous RG parameters in some theory. And then what typically happens is that we have a second-order phase transition where we flow to a conformal theory, and often we have a line of second-order phase transitions that ends at some multi-critical point and becomes a line of first-order phase transitions. So that's obviously one thing that can happen even without having all these discrete parameters. But in the context of conformal windows, we do want to have also these discrete parameters, which means in some sense that the CFT along this line of second-order phase transitions also varies. So that will give us a richer array of possibilities compared to just this usual case, which appears in the study of standard phase transitions. So that's the setup that I'll be discussing here. So are there any questions about the general setup? Yes, please.
Do you allow for an intermediate phase where you have a little bit of pions and a little bit of conformal?
So what?
With some pions on top, like something that breaks some of the symmetry, but
right. Yes, sure. So one possibility is that, that you could have a conformal theory with some extra free fields at low energies. So that's indeed one type of possibility that happens. So this will not happen in any of my examples, but yes, in general, one could have some. But I'll just refer to that as a general it's still a CFT in some sense with some free sector in it. So yeah, but definitely that's also possible. Well, without large n, then it's really just a discrete family of theories. I mean, I don't know of any way to really make sense of questions like this in the context of like non-integer numbers of flavors.
I understand, but you could change the flavors in some cases continuously by adding masses. I don't know.
Right, but in the massive theory, there's no transition. I mean, so then, I mean, yeah. So I'm not sure.
Well, if you're in the conformal window, if you're one flavor,
would you please use the microphone when you ask questions?
Sorry, just to turn it on. There's a button. Yes, turn on. Yeah.
Okay, like this.
This.
If you're one flavor in the conformal window, and if you remove that flavor, you're going to be in the confined theory. Then if you add a mass to that flavor,
right,
you're going to induce that phase transition by adding changing a continuous parameter or something. Would it be the same nature? I guess.
No, I don't think it's going to be of the same nature. Well, we can discuss that in each of the scenarios that I'll describe, but there's no, I don't know. Well, yeah, it will depend a bit on the precise way that the conformal window ends. But yeah, definitely each scenario for the end of the conformal window will also map into some scenario for what happens in this massive theory. But I think we may as well just study it in the massless case first. Yes, please.
So in practice, in the latest calculation, NF is actually a continuous number.
Well, not really, because of course for non-integer values of an f, of course you have phase problems and so on. I mean, so there are much more subtle issues. I mean, so yeah, in some senses it is discrete, but yeah, but there are all these phase problems that you have to overcome and so on. So yeah, so it's for some questions that's true, but I'm not sure if for this complete setup if one can really treat an f as a continuous parameter. Okay, so let me move on to describing what are all the possibilities for how conformal windows of this type can end. So we'd like to start from the conformal window side and then ask what could go wrong when we change this continuous parameter nf over nc. Of course, one possibility is that the theory could just become free. I mean, that's what happens in QCD4 at the upper end of the conformal window. The theory just becomes free. But of course, in QCD4, at least, we know that that cannot happen at a smaller number of flavors, just because the theory has a non-trivial beta function then. Another thing that can happen in some cases is that the theory could become free in some other set of variables, and we know that that's what happens in supersymmetric QCD, where we have some dual description of the same CFT in some other set of variables that becomes free at this critical value. But at least for QCD and for the other examples that we'll discuss, we don't know any candidate for what this alternative free theory could be. So we believe that that is not what happens at the end of the conformal window, but in general, that is always another possibility for what could lie at the other end of this conformal window. And of course, in that case, this transition is well understood. It's just the transition of turning on a small beta function here. But I'll focus on other cases here. So what else could go wrong from the point of view of this conformal field theory? So this conformal field theory only has irrelevant operators. Of course, that's why we can flow to it in QCD, in massless QCD, without any fine-tuning. So the lowest dimension operator is just a trace of f nu squared, which starts at a dimension slightly above 4, which you can compute in perturbation theory. And then the next operators are 4 Fermi operators, whose dimension starts around 6 here. And then as we change this parameter x, all of these dimensions are continuously changed, and all these operators mix together. And then one thing that could happen at the end of this conformal window is that possibly one combination of these operators could become marginal, so its dimension could go to 4 in the 3 + 1 dimensional case. And one could ask what happens then, and this scenario was suggested by many people about the end of the conformal window, in particular in this paper by Kaplan et al. So what happens if an operator goes down in its dimension and becomes marginal? So of course, as long as the operator is irrelevant, then the beta function just looks like this with a positive slope, and we have an attractive fixed point. Wherever we start, we just flow to that fixed point, where the slope of the beta function is, as usual, related to the dimension of this operator minus d. So that's the usual story of the infrared stable fixed point that we believe we have for larger values of x. And then naively, what one may think is that when we cross this place where the operator becomes marginal, perhaps the dimension of this operator would become negative, and then all that would change is that we have this negative slope of the beta function, and then this theory would become repulsive at low energies, so that would explain why we don't flow to that fixed point anymore. So that's a priori one possible scenario, but in fact, this scenario is not what generically happens when an operator becomes marginal. And the reason for that is that before the dimension of the operator goes down below d, it hits the marginal value, delta equals to d. And what the beta function actually looks like there generically is of this form, because we know that at that point, the beta function vanishes because we have a fixed point, and its derivative also vanishes because delta is equal to d. But generically, the second derivative of the beta function will not vanish at that point unless there are some extra symmetries that ensure that. But in QCD and in the other examples I'll describe, there are no such extra symmetries. So in those examples, we expect that if an operator becomes marginal, the beta function should behave like this. And this completely changes the story about what happens when the dimension of the operator goes down. So because when the dimension hits d, we have this shape of the beta function, then by continuity, what this implies is that when we're slightly above this point at x bigger than xc, then we do still have this stable fixed point where the operator has a dimension that's slightly above d. But again, by this continuity, we know that in this range, we actually have two different fixed points, one infrared stable one and one infrared unstable one, where the dimension of the analogous operator is less than d. And the full phase structure of the theory looks like this, where we have these two separate fixed points. And we still flow to this fixed point if we land close to it, but we have also this other fixed point. And then what happens if we continuously vary our parameters, in particular this parameter x, is that at the critical value, we would have this form of the beta function. And then as we continue modifying it, we move over to this shape of the beta function, where these two fixed points merge and annihilate. And we no longer have any fixed points of the beta function. So instead of having some unstable fixed point, as one would naively expect, we actually see that there are no fixed points at all. And this is what's known as the conformal field theory merger scenario for how conformal windows can end by an annihilation of two fixed points. And this is one generic scenario for how conformal windows can end. And of course, in this case, when we go for x smaller than nc, we don't have a fixed point anymore, and we just continue flowing until we reach some, well, presumably the flow all the way to minus infinity implies that we have this other confining symmetry breaking vacuum. So this is a well-studied scenario for how conformal windows can end. And in particular, if x is slightly smaller than xc, we have this very small RG flow, which is a slow RG flow, which is sometimes called Miransky or BKT scaling, or in other contexts, a walking RG flow. So this is obviously one viable scenario for how conformal windows can end. But what I'd like to stress in this talk is that there are also other possible scenarios which are equally generic. So one should not focus just on this scenario, but one should keep one's mind open and really test which scenario actually happens for the end of the conformal window in a specific theory like QCD. So this is one scenario. Now one could ask what else could go wrong from the point of view of the conformal field theory. What else could cause this conformal theory to stop describing the infrared behavior? And from the point of view of just the conformal window, just the conformal field theory, it turns out that there's one other possibility for how a conformal window can end. So in addition to looking at the beta function, we could also look at the effective potential of our theory as the function of the vacuum expectation values of various operators. So in the QCD, for example, we can look at the effective potential for the mesons. Now we can compute this effective potential in the full QCD theory, but we can also compute it just in the fixed point that we flow to. And at the fixed point, the form of this effective potential is actually almost fixed by conformal invariance. So if the meson operator has some dimension delta m, then the global symmetries and conformal invariance tell us that the effective potential for this parameter has to be proportional to the meson vev raised to some specific power times an arbitrary dimensionless constant c. Now, of course, typically when we flow to this fixed point, we expect that c should be positive because, of course, the CFT vacuum should be a stable vacuum. But it turns out that one thing that can happen when we just follow a family of conformal field theories as we change these continuous parameters is that this parameter c could become negative as we continue following this family. And we'll see an example of this in a few minutes. And of course, if that happens, then what that implies is that for x smaller than xc, we just have this stable vacuum at the origin. But then at x equals to xc, this vacuum becomes almost unstable. And as we go beyond, for x smaller than xc, this vacuum becomes unstable. Of course, in the full QCD theory, we don't have just this specific power law. We have also higher dimension operators that affect this effective potential. So the effective potential would eventually stabilize. And we have a situation that resembles a second order phase transition, where for x smaller than xc, we would have a different vacuum somewhere nearby. So in this scenario, unlike the previous scenario, the CFT does continue to exist, albeit as a non-unitary theory, even beyond this transition, but we just start flowing to some other minimum of the effective potential. So this is a second possibility for how the conformal window can end in general. Now, there are actually two additional possibilities for how this conformal window can end if we consider the full renormalization group flow from the weakly coupled theory at high energies to low energies. So one thing that can happen in the context of this flow is that this alternative conformal theory could start playing a role. So I already mentioned that if we have a CFT merger, then this implies that at least when we get close to the transition, there's actually another unstable fixed point appearing in the full space of theories. And in the conformal merger scenario, that fixed point is actually pretty close to the original conformal theory that we flow to. And then one thing that can happen as we change our parameter x is, so if we believe that so there is some operator which is the lowest dimension operator, which controls the RG flow. So if we imagine first doing the RG flow in all the other operators and then considering just the RG flow as a function of this coupling, which is the most relevant coupling, then we can imagine that for some range of i's of x, we land here and continue flowing to the original fixed point that we had, but then perhaps there could be some critical value of x where we actually flow to this other fixed point instead, this unstable fixed point. Of course, that requires one fine-tuning, but as we change the parameter x, we exactly can accommodate such a fine-tuning of one parameter that would lead us to flow to this alternative fixed point. And then as we continue flowing, then the RG flow would just lead us to flow away, just like in the CFT merger scenario. So this is what we call the alternative conformal field theory scenario, where the critical value of x, even though the CFT continues to exist, we stop flowing to it and we start flowing somewhere else. And the scenario seems at least as generic as the merger scenario, in the sense that if we have a merger and we approach this merger, then it's possible that we're on the right-hand side of this and then we would continue flowing to the original CFT, but it's also possible that we're on the left-hand side of this and then even before we hit the merger, we would hit this other conformal field theory first and flow away. So the scenario definitely seems at least as generic as a merger scenario. And of course, it's also possible that this alternative CFT could be far away. So in some sense, this is maybe even more generic. So this is a third scenario that can happen, and we'll see that it does happen in some examples. A microphone, sorry.
It's more like a property of boundary conditions on your flow, no? Or
that's right. So this scenario is
I mean,
we're discussing flows from a very specific UV completion of just the UV-free QCD to low energy. So indeed, this scenario is not intrinsic to the low energy theory, but we're following a family of RG flows from a specific UV starting point, and then in that specific family of RG flows, we could have this alternative CFT scenario.
Because usually there are many cases where both are perturbative and you have some domain from which you flow.
Exactly.
There's always
Exactly.
some places where you flow away to
Exactly.
massive phase. Right?
Exactly, right. But the question is, say,
But that's
specifically for
definitely-
QCD, what happens when we change the number of flavors? And then it could happen that in that very specific RG flow from QCD, we would have this thing instead of having the merger. So we would first, even before the fixed points merge, if they do merge, we would flow to this alternative CFT and then start flowing as well. And this has very different predictions for measurements on the lattice, as I'll describe in a moment.
Okay.
So a final scenario is analogous to what would be a first-order phase transition in statistical mechanics. Namely, we have this effective potential, say, for the mesons. And another thing that can always happen and that is very difficult to rule out is that in this effective potential, we could just develop some other vacuum that's far away from our CFT vacuum. So even if the CFT is perfectly fine for a large range of values of x, it could be that at some specific value of this parameter x, the effective potential develops another vacuum, say with meson vevs of order of the QCD scale, and then this other vacuum could start having lower energy. And then, of course, we would just have the analog of a first-order phase transition, where instead of flowing to the CFT, we would just flow to this other vacuum. So this is another scenario which can happen and does happen in some examples. And, of course, it could also happen, in principle at least, in QCD. So we have these 4 different scenarios for how a conformal window can end. 2 of them are intrinsic in the sense that they depend on properties of the CFT that it flows to and can be analyzed just from the low energy point of view, while the other 2 are extrinsic in the sense that they depend on the full RG flow that we're studying, whether that full RG flow leads us to the CFT or if it just leads us somewhere else. And the scenarios can be distinguished, as I'll describe in the next few slides, by the behavior of these RG flows as we approach this end of the conformal window. So I'll describe in the next few slides exactly how we would distinguish these scenarios by, say, lattice simulations of this family of theories, or this family of renormalization group flows. And a request to the lattice people is to try to measure the end of the conformal window and QCD and related theories precisely enough so that we can distinguish these 4 different scenarios and figure out what actually happens in QCD. Of course, that requires doing these simulations at large values of n because we need to be close to this transition, and this parameter x really only becomes continuous at large n. So this is not an easy request, but I hope that still lattice technology will enable this to be studied. So in order to do that, let's describe what would be the implications of these 4 different scenarios for measurements that one could do, say, in lattice simulations of QCD. So again, the traditional scenario, which as far as I know is more or less the only one that's actually analyzed in the lattice literature, is this scenario that we would have this CFT merger. So in this case, when we simulate these theories, sorry. Yes. Yes. Yeah, of course. The same thing can be analyzed in many other theories.
And I mentioned adjoint QCD because maybe such theories could be studied on the lattice with these twisted Akuchi-Kawai, which have access to very, very large n.
Right.
And maybe that is a better place to start for lattice simulations. I don't know. I mean,
that's a good question, but if you only have adjoints, then this is not a continuous parameter. So you want to have adjoints and also some small number of flavors so that you can really have this continuous parameter, and that's, of course,
very
goes
good
back
point.
to all the other problems.
So forget about my idea.
Yes, so thank you. Okay, so in this CFT merger scenario, what happens as we approach this critical point, so we, above x critical, we just flow to this fixed point, but this flow becomes slower and slower as we approach the end of the conformal window because the dimension of this operator approaches d, so the flow becomes slower and slower. So that's what we would see if we analyze x approaching xc from above. If we have x approaching x from below, then as I mentioned, we have this, again, very slow renormalization group flow because the beta function is very slow here. And in this case, we actually have this very large gap forming between the infrared scale, say the scale of f pi in the Carrel-Lagrangian that you would get at low energies, and the high energy scale. So they're related in this case by this famous exponential factor. Because of this very slow RG flow. So this is what's known as Miradsky and BKT scaling, which, of course, Igor also mentioned this BKT transition in his talk. So this is the maybe more traditional scenario. But the other scenarios are also possible. So if we have this CFT instability scenario, So in this case, as we approach this critical value from above, we wouldn't really see anything special going on. I mean, so this effective potential develops in almost flat direction, but okay, in the full theory, it's not really a flat direction, so nothing too special would happen when x approaches xc from above. In particular, the RG flow would not really slow down when this happens. Now, when x approaches xc from below, in this case, then we would have this other vacuum, and the infrared scale, say the scale of f pi in the low energy theory, in this case, would scale as a power law of xc minus x. So that would be controlled by the dimension of the meson operator and by the dimension of the sleeting correction to the effective potential. So it's easy to see that these parameters would control the relation between the infrared and the UV scale. And in principle, on the lattice, it should be possible to measure this ratio between the IR scale and the UV scale, and so to compute this, well, to see if we are in this scenario and to measure this parameter alpha. So this is what we would have in this CFT instability scenario. The third scenario I described is this alternative CFT scenario, where at some critical value of x, we flow to this other fixed point instead of to the original fixed point that we wanted to have. So in this scenario, the flow to the CFT again slows down when we approach the critical point, but now it slows down for a completely different region. It's not that the dimension of some operator becomes small, but just that we happen to land close to this other fixed point, and of course that slows down the RG flow, but in a different way. I mean, we'd first have a slow RG flow, then a faster RG flow as we go to this fixed point, and then again, we would just end up at this other fixed point. So here the flow flows down at some intermediate range of scales instead of at low energies. So that's something that, again, can hopefully be seen in lattice simulations. As we approach x equals xc from below, then again, we have this relatively slow RG flow, and then we flow somewhere else. And one can compute that also in this case, the ratio between the IR scale and the UV scale would be given by some power of xc minus x, when in this case, that power would be determined by just the dimension of the leading relevant operator at this alternative fixed point. So again, this is something that hopefully can be measured in lattice simulations. And finally, in this fourth scenario, where we have another vacuum, so in this scenario, like in first-order phase transitions, nothing really special happens when we approach the transition from either side, but we just first flow to this fixed point, and then for x smaller than xc, we would just flow to this other vacuum with a non-zero expectation value that immediately jumps from 0 to a non-zero value without going to 0 as x approaches xc. So again, this is something that should be easy to identify in lattice simulations. So those are all the scenarios and how to identify them. Of course, unfortunately, we don't know how to identify which of these scenarios happens in QCD, neither in 3+1 dimensions nor in 2+1 dimensions, because the theory there is strongly coupled and hard to control. But hopefully, lattice simulations can actually simulate this theory very close to this transition point, and see which of these scenarios actually happens. Of course, it's challenging on the lattice because we have to go to large n in order to be close to this transition, and of course, to be with massless fermions. And in some of these scenarios, we also have to investigate a very large range of scales, which is also, in practice, difficult on the lattice. But at least in principle, this question can be answered on the lattice, and so far, that's really the best tool that we have for testing these scenarios. Yes, please. Yes.
Why are they not sensitive to exactly which lattice action you use? That is, couldn't different lattice actions, which all flow to the QCD and the IR, give you different initial conditions in the UV?
Right. So in general, yes. But so I'm imagining that I'm taking my lattice theory so that it does get to the continuum flow already at a high enough energy so that all the other operators die off. So indeed, you'd want to get to the continuum region at a very high. So that's also another reason why you need this very large range of scales. So of course, if you don't have a large range of scales between the lattice scale and the QCD scale, then indeed the results could also depend on the precisely what happens at the lattice scale, which other irrelevant operators you have, and so on. But this question becomes well defined if 1 over a is much bigger than lambda QCD, and then again lambda QCD has to be much bigger than this infrared scale. So you really need this very large range of scales, and then it becomes a well-defined question that's intrinsic to QCD4. But yeah, otherwise on the lattice, indeed, you could be sensitive also to irrelevant operators at the lattice scale. So yeah, thank you. Now, another way to possibly test these scenarios could be by doing a bootstrap analysis of this conformal theory, the fixed point of QCD. So far, no bootstrap analysis has found these fixed points, but in principle, it should be possible to find these fixed points by a bootstrap analysis. But of course, a bootstrap analysis just of the CFT cannot really tell us which scenario happens, because that depends, as we discussed, on the full RG flow from QCD, from the weakly coupled high energy theory to low energies. However, in the bootstrap, we could in principle see if there is a merger, so if delta goes to D. So if there is a merger from the CFT point of view, then we could have the merger scenario, or we could have some other scenarios. But of course, if no operator goes down to D, then that would rule out the merger scenario. And it would be interesting to see if by bootstrap methods, one could also test this CFT instability scenario or not. Again, in principle, this should also be amenable to some bootstrap type analysis. But again, that will only tell us, that can only rule out scenarios. It cannot really tell us by itself which scenario actually happens in QCD. So in the rest of this talk, instead of discussing QCD, I'll describe 3 other examples of conformal windows, where in these examples, the conformal window will be weakly coupled so that we can actually compute everything that I described and see which of these scenarios actually happened. And in some of these examples, we'll also have extra parameters to tune, and then we'll see that for some values of these other parameters, we have one scenario, and for other values, we have another scenario, illustrating that all of these scenarios are generic. So are there any questions before I move on to specific examples? Okay, so my first example will be naively very similar to QCD, namely it will just be 3 + 1 dimensional QCD, where we add also some number of massless scalars in addition to the massless fermions that we know and love. So what happens if we have some number of scalars? Well, naively, not too much changes. I mean, so of course we have this diagram. If we add some number of scalars, the theory would still become asymptotically free for some critical value of the number of scalars plus the number of fermions. And we'd still expect to have this conformal window, which is weakly coupled and then becomes strongly coupled. So naively, one would think that nothing changes. But in fact, that's not true, because when we have also scalars, then at least in the weak coupling region, we also have extra phi to the 4th couplings that are marginal and that can and will be turned on. And then one has to analyze what happens to the flow of these extra phi to the 4th coupling. So we're forced to analyze not just the naive QCD theory, but a theory where we also have these phi to the 4th coupling. So the Lagrange, so in the, and this was analyzed in several papers a few years ago by Bedini et al. And by Appelquist et al. So the theory we're forced to analyze now is a theory where we have Young-Mills plus these massless fermions and these massless scalars, whose mass, of course, we have to fine-tune to 0, but so we just fine-tune that to 0. But then in addition to that, we have these 2 types of 4 scalar couplings, either a sort of a single trace in flavor space, phi to the 4th coupling, or a double trace in flavor space, phi to the 4th coupling. So we have these 2 independent couplings that, when we approach weak coupling, are both marginal. And we have to follow what happens to their renormalization group flow. So the limit that I'll be considering now is a limit where we have NS scalars, NF fermions, and we'll take NS, NF, and NC all to go to infinity, but with fixed ratios that I'll denote by XS and XF. And then we also have these 3 couplings, G, H tilde, and F tilde. So in the large N limit, these are the combinations that we need to keep fixed in order to have a non-trivial theory. So we have these 3 parameters. And there is some range of initial values where all 3 of these parameters are asymptotically free, so that we have a well-defined starting point in the UV. And then we have these 3 parameters we can turn on starting from the UV. So we have 2 renormalization group invariant combinations of these 3 parameters. And so the question about the conformal window now becomes, in some sense, a question about a 4-dimensional space of theory. So we have these 2 discrete parameters of the ratios of these numbers, and we have 2 extra parameters coming from seeing which renormalization group flow we're following from the UV theory. And we'd like to ask, what do we get in the IR as a function in general of all 4 of these parameters? So that is a well-defined question. And again, we'll see that we have a conformal window in some range and no conformal window in some other range. And we'd like to see how it ends. Now, the surprising thing is that in this case, we'll see that the conformal window can actually end at weak coupling when we still have control. So first of all, in order to be at weak coupling, of course, we want to be close to the edge of the usual conformal window. So we want the number of scalars plus the number of fermions to be close to this asymptotic freedom point. So in that case, what happens is that the flow of the gauge coupling is basically independent to 1-loop and also 2-loop orders of these other phi to the 4th couplings. So the gauge coupling just flows to some weakly coupled fixed point independently of the other parameters. And then along that RG flow of the gauge coupling, we can study how the other 2 parameters, these 2 4-scalar parameters, H and F, flows. And it turns out that if we start from a very small number of scalars, smaller than 0.073 times the number of colors, then the renormalization group flow of these other 2 parameters actually has 4 fixed points. So one of these fixed points is completely stable, so that we would generically flow to it. That's this fixed point F3. And then there are two other fixed points where we have to fine-tune one parameter, and one other fixed point where we would have to fine-tune two extra parameters to flow to it. So this is what the RG flow looks like. Again, this is all weakly coupled, and in this range where XS is smaller than 0.073. But it turns out that when we increase the number of scalars to beyond 0.073 times the number of colors, again, still staying very close to this asymptotic freedom bound, the flow changes in the space of these two phi to the fourth couplings. Two of these fixed points merge, so they just continuously merge as we change this parameter XS. They merge and annihilate, just like we discussed in the CFT merger scenario, and we're left only with two fixed points, both of which are unstable. So that generically, in this case, of course, we would no longer flow to any fixed point. So that can all be seen just by a direct perturbative analysis. So we can now consider a sequence of theories where we gradually increase the number of scalars and also decrease the number of fermions so that we stay, say, at the same distance from the asymptotic freedom point. And then we choose some specific values of these phi to the fourth couplings in the UV, or more precisely of the RG invariant combinations of these phi to the fourth couplings and the gauge coupling. And then we'd like to ask, as when we increase this parameter XS, how do the RG flows behave? So one option is that we continue flowing to this infrared stable fixed point F3 all the way until that fixed point merges and disappeared. So that's one logical option. And in that case, we would have what we call this CFT merger scenario. But another scenario is that when we continuously change this parameter, we could flow to one of these other fixed points at some fixed value of x. Say we could flow either to this fixed point or in this fixed point, which both require just one fine-tuning. And then we would have an example of this other alternative CFT scenario. And of course, the other two scenarios would imply that we actually don't flow, that the flow actually ends by forming another vacuum somewhere else. So that's also a possibility. And all of these possibilities in this example can just be tested analytically, because we can compute exactly the beta functions. We can compute exactly the effective potential. So in this case, the analog of the Meson expectation value is just an expectation value of phi dagger phi, which can just be computed perturbatively. And we can check which scenario happens in this example. So I won't bore you with the actual computations, but when analyzing the effective potential, you can show that actually it does not develop any vacuum elsewhere. So we don't have either of these scenarios where we have an alternative vacuum. But we can realize both of the other scenarios. So again, we have now a two-dimensional family of RG flows depending on these continuous parameters, which we can take to be, say, the values of H and F when the RG flow of the gauge coupling reaches some specific point. So these are RG invariant combinations of the UV parameters. So what's drawn here, so there is so the range bounded by these blue dots is the range where the theory is asymptotically free just by computing the beta functions. So that's the range where we have a well-defined UV starting point in the case that the number of scalars is 0. And then we gradually increase the number of scalars as compared to the number of fermions until we approach this value where the fixed points merge, which is approximately 0.072. So in that range, we have a smaller, so the range of asymptotic freedom is the range, so the range of these black dots is where the theory stops becoming asymptotically free. So that's not an interesting range from this point of view. But in the other range, we still have an asymptotically free renormalization group flow. And then it turns out that in some region of this parameter space, we continue flowing to the CFT all the way until the merger. But in some other region of this parameter space, we actually flow to one of the alternative CFTs before we hit this merger of the fixed points. So we realize these alternative CFT scenarios. And actually here we can realize flows to either one of these other fixed points that can exist. So in this bottom region, we flow to one of these fixed points. And there's a very small region here, which is hardly visible in the plot, where we flow to the other fixed point. So this is an example where we can see that both of these scenarios, the CFT merger and this alternative CFT scenario, are both realized in a measure, in a non-zero measure region of the parameter space. So any questions about this example?
So yeah, I'm confused. You said the alternative CFT had one extra relevant operator.
That's right.
So you need an extra
so we tune
tuning.
this parameter x until we hit, at some value, we hit this other fixed point, and then we go to its other side so that we just flow away. So in some sense, when we describe the other parameters, we land here, but then as we change x, at some point we land on this point, and then we just have the flow from the other side of it. So that's exactly this extra parameter of the relative number of scalars, which we're changing, and then we can tune to this value where we hit this alternative CFT.
Are these exactly aligned?
No, I don't think so. Aligned in what sense? I mean, even parallel to each other?
For a fixed H, are they
No, I don't think so. I mean, they're approximately aligned, but yeah, but not exactly. I mean, of course, this is truncated to leading order in the large limit and so on, but yeah, but yeah, they're not exactly aligned, I think. Any other questions about this example?
This was a bit fast, so I didn't.
Yeah,
so
sorry.
Inside the blue dots.
Yeah, inside the blue, so the theory is asymptotically free inside this bigger region, the region that's not black. In this region, there is a well-defined RG flow, and we can just ask what happens to the RG flow as we change x. So inside this, so for small values of x in this whole region, we flow to the fixed point. But then when we increase x, eventually we only flow to the CFT in the region that's bounded by these red dots. So outside of these red dots, somewhere in the middle, we flow to this other CFT, and then we start flowing far away.
What was x now?
X is the number of scalars. So we're changing the number of scalars while still keeping the one-loop beta function fixed. So we're decreasing the number of fermions and increasing the number of scalars.
Oh, sorry. So you're both changing number of fermions?
Yeah, and keeping the one-loop beta function fixed. Just, of course, we could also examine various other directions, but this is just some specific direction in this 4-parameter space of theories that I mentioned. Any other questions? Okay, so my second example, I'll discuss a completely different theory, just QED in 2 + 1 dimensions with a Chern-Simons term. So we have a Maxwell term, we have a Chern-Simons term with some level k, and then we'll couple that to just NF scalar fields. And then in general, we could have any phi squared, phi to the fourth, and phi to the sixth couplings of these scalar fields. So this theory is weakly coupled if either this Chern-Simons coupling k is large or the number of flavors NF is large, and then we have a 1/NF expansion. And in particular, in order to have a continuous parameter, we'll again take the limit. So in this case, the number of colors will stay 1. It does not go to infinity, but these two discrete parameters, k and NF, can be taken to infinity with a fixed ratio kappa. And in order to have a well-defined family of RG flows, then we start at high energies by taking this phi to the sixth coupling to 0. So since we have a Maxwell term, then at high energies, the gauge interactions go to 0. So we can just have a free theory at high energies, which is well-defined for h = 0. And then as we go down in energies, eventually we hit this scale. So for large NF, the relevant scale is e squared times NF. So at that scale, the gauge interactions start becoming important. And we could also generate phi to the fourth and a mass at that scale. And then if we fine-tune these parameters, we could land at various interesting fixed points. And we'd like to ask, do we end at, or for what range of values of this parameter do we actually end the RG flow at a fixed point or not? So that's the question we want to analyze. So if we only fine-tune the mass term, then this renormalization group flow, so for very large k, this is very weakly coupled, so we would just end up at the usual critical fixed point, which is just the critical UN model and the limit that k goes to infinity. But we're interested in analyzing this also for small values of k. But if we just fine-tune one parameter, then these flow to what are called Chern-Simons matter fixed points. So these are sometimes called the critical boson Chern-Simons matter fixed points. But for the purposes of this talk, we're actually not interested in this RG flow, but we're interested in the flow where we fine-tune both the phi squared and the phi to the fourth coupling to end up at a tri-critical point. So this Chern-Simons matter theory, so I should have said that formally for energies below the scale lambda, the Maxwell term becomes unimportant, and we just have a Chern-Simons matter theory that can be exactly solved in this limit of large k and large NF. And then that theory has also another fixed point, which is a tri-critical point for which we have to fine-tune both the phi squared and the phi to the fourth theory. That theory is also weakly coupled in this limit of large k and large NF. Of course, if k goes to infinity, that theory is just the free scalar point. But in general, there is a family of theories connected to it. And we'd like to ask if we follow this family of RG flows, always fine-tuning these two parameters so that we try to end at a non-trivial fixed point, then what happens? Can we still flow to a fixed point also when we change this parameter k over NF, or do we stop flowing to a fixed point at some point? So the issue in this case is, once again, that because we have a weakly coupled theory, we have this extra parameter that is close to being marginal, which is the coefficient of this phi to the sixth coupling. And actually, if we go all the way to infinite number of flavors, then this parameter is actually exactly marginal. So here we'll be interested in taking NF large, but not all the way to infinity. And if it's large, but not all the way to infinity, then this parameter does have a small beta function that can be exactly computed. And so we can analyze exactly what this phi to the sixth coupling does. And so this is the exact form of the beta function, which depends on this continuous parameter kappa, which I remind you is just the ratio of the Chern-Simons level to the number of flavors. And it turns out that for some range of values of this kappa up to this very specific value, then there is an infrared stable fixed point for this phi to the 6 coupling. And we have a flow from our theory to this fixed point in the context of just the Chern-Simons matter theory now. It's much, I mean, in that case, this flow can be exactly solved. It's not known how to solve it exactly if we also have the Maxwell coupling. So in that range, the Chern-Simons matter theory that we have at low energies has this non-trivial fixed point. And then when we get to this boundary value, this fixed point, again, if we just analyze the low energy CFTs, this fixed point merges with another fixed point at a double zero of this beta function that I had on the previous slide and disappears. And our question is, again, if we start from this very specific high energy theory, which is just this free Maxwell Chern-Simons matter theory, when we start from that theory and vary this parameter kappa, do we continue flowing to this fixed point all the way until it merges with another fixed point, which is what we call this CFT merger scenario, or do we have one of the other scenarios? So to check that, again, we have to carefully follow these RG flows in the full theory, and we also need to compute the effective potential for this operator. So in this case, the lowest dimension operator is, again, just phi dagger phi. So we'll call eta this normalized phi dagger phi operator, and we have to compute the effective potential for this operator. Now, this effective potential was computed almost 3 years ago in the low energy Chern-Simons matter theories by DiPietro et al. So that is in essence a computation of the effective potential at this tricritical fixed point that we want to flow to. And what they found is that at low energies and for positive vacuum expectation values of this phi dagger phi operator, the effective potential takes this form. So it's just proportional to this phi to the 6 coupling, which is just in some sense just the classical form of the effective potential. So naively, one may think that this means that the flow is always stable. But actually, it turns out that the value of this phi to the 6 coupling at the fixed point actually changes sign when we change kappa, so that there's a critical value of kappa, which is close to this value where we have a merger, but it's below it. So there's this critical value 0.0361, where as we cross that point, the value of this phi to the 6 coupling at the fixed point goes over from being positive to being negative. So from just the CFT point of view, this means that we can have this CFT instability scenario where the CFT just develops a negative effective potential so that we do not expect to flow to it anymore. But again, our question is what happens in this case for the full RG flow starting from the Maxwell Chern-Simons theory, where we could also have interesting things going on at the scale of the gauge coupling. So for that, we have to analyze the full effective potential in this theory to see if maybe we would have some other low energy vacuum. So yeah, just a second. I'm almost done with this example, and then I'll take questions. So we computed the full effective potential in this theory and the large unlimit. And what we find is that, indeed, the full effective potential, it doesn't have a vacuum somewhere else. It only has this vacuum that, when we're close to the fixed point, is very close to the origin. So this is the log of the effective potential, essentially. And it has this one minimum close to the origin, which is the one that would be expected in this CFT instability scenario. And it does not have a minimum anywhere else. So for this family of RG flows, we do realize this CFT instability scenario, where up to this critical value of kappa, we flow to the CFT, but below it, we flow somewhere else, even though there is still a non-trivial fixed point of the normalization group. So any questions about this other example, Victor?
Why was there no quadratic term in this effective potential?
So I just fine-tuned to 0. So I fine-tuned to 0 at low energies, both the phi squared and the phi to the 4th term. So at high energies, I fine-tuned them to some value that depends on the gauge coupling, but I fine-tuned them so that at low energies, I flow exactly to this non-trivial tricritical fixed point. So I can always make that fine-tuning. And I continue doing the same fine-tuning all the way until something interesting happens. So I try my best to still flow to that CFT by fine-tuning this to the best of my ability. But then after we cross this transition, we see that no matter how hard I fine-tune, I cannot flow to this fixed point anymore, but I flow to this other vacuum that's nearby.
No operator, no other operator becomes marginal.
Indeed, no other operator becomes marginal, but the effective potential does just become negative at this critical value. So again, the effective potential, okay, I didn't draw this on this slide, but just the effective potential on the CFT becomes negative. So the CFT, in some sense, becomes non-unitary, but it just does that continuously. And we stop flowing to this.
Why is absence of some terms in the effective potential of CFT, why is it the same as tuning coefficients of operators? You say the
Well, it's the same thing, because at the CFT, I'm tuning all the relevant operators to 0. So that's the same as saying that in my effective potential, I would not have these terms. I mean, so that's the same statement just from the UV and from the IR points of view. So yeah, Zal. That's right. It is existent. It's just non-unitary anymore. So the CFT continues to exist even below this transition. We just don't flow to it from the UV. And it is an intrinsic property, indeed.
Wait. Does the CFT? Yeah.
No, in this case, no. It's the vacuum of the CFT that becomes unstable. It's not some specific operator, but the vacuum becomes unstable because we have this effective potential becoming negative.
But Ofer, in CFTs where there is an intrinsic non-unitarity, let's say phi cube theory,
right?
Okay, some scaling dimensions become complex, for instance.
That's right. So also in this case, but here it happens because the vacuum becomes unstable. I mean,
but that's what Victor said should be true. That like a signal of this potential becoming negative could be that some scaling exponents become imaginary.
Oh yeah, sure, definitely. But they would start developing a very small imaginary part when we cross this transition. That's right. But again, that's from the CFT point of view. But from the point of view of RG flow, we just don't flow there anymore. We flow somewhere else, and that's what I'm interested in for this talk. Okay, so I'm afraid I'll have to rush a bit through this final third example. In this third example, we're discussing, again, just to have a wide range of examples, we're discussing a family of theories that has a dual holographic description, which is weakly coupled and weakly curved. And to simplify things, we're just taking the holographic dual to have just gravity plus a single scalar field. So in that case, whenever the scalar potential is minimum and it has some extremum, then we know that that describes, in general, a dual fixed point in the dual field theory, which has some central charge depending on the value of the potential there. And we can discuss renormalization group flows between these fixed points just by looking at classical solutions to this gravity action, where the scale factor of the changes in this way, and where also this scalar field changes as we move in the radial direction. So these types of families of CF. So for simplicity, I won't discuss any top-down examples of this, but we'll just imagine choosing by hand some family of potentials in the bulk. And then it turns out that in some cases, as analyzed by Kiritsis et al., in some cases, so this is the scalar potential here. It's always negative, but we could have, say, a maximum of the scalar potential, which in this case means we have a relevant operator, and then we could turn on that relevant operator and flow to some other CFT where the same operator would become irrelevant. So this is like the standard picture of holographic renormalization group flow. And in order to discuss the possibility of CFT mergers in this scenario, for instance, we can imagine a scenario where we modify the potential such that a minimum and an adjacent maximum of the potential join together and annihilate just as we change the shape of this potential. And in that case, we can ask if we have an RG flow starting from some other CFT flowing there, do we continue flowing to that theory all the way until we hit this merger or not? So I'm afraid I don't have time to discuss the details, but yeah, if we have a CFT merger, then that would mean that we flow to this theory all the way until the fixed points merge, and then we start flowing somewhere else. In principle, we might imagine that we could also have an alternative CFT scenario in this holographic scenario where we flow to a maximum instead of to a minimum, but it's easy to show that that's actually impossible. But what can happen is that we could have this alternative vacuum scenario where we have one RG flow landing at this theory, but we could have, for the same UV theory, it turns out that in this holographic setup, even though it's somewhat surprising, we can have, for the same UV theory, two separate solutions to the bulk field equations, which end up in different CFTs and the IR with different central charges and operator dimensions. And then the question just becomes, which of these RG flows has a lower energy, so that we would know if our original CFT continues to dominate until we reach this merger, or do we develop another vacuum that has a lower energy and which describes a flow to a completely different CFT. And it turns out that, again, I won't have time to discuss any of the examples, but in many examples, we find that, indeed, there is this other RG flow which takes over before we hit the merger. So even though, in principle, the CFTs, we could have had the merger scenario, we actually flow somewhere else before we hit the merger. But again, for a different range of potentials in the bulk, we do have the CFT merger scenario. So in this case, both of these examples are also possible. So let me just summarize, since I'm out of time. So I discussed in this talk 4 possible scenarios for how conformal windows can end. And all of these scenarios seem to be generic in the sense that we don't need any fine-tuning to get any of these scenarios. So of course, I mean, there may be a fine-tuning that's needed to flow to these fixed points to begin with, so that I'm sort of taking for granted. But beyond that, in the space of theories, we don't need any fine-tuning to get any of these scenarios, so they all seem equally generic. And I reviewed 3 examples where we saw that in some regions of the parameter space, we realize each of these 4 different scenarios. And of course, many additional examples can also be analyzed. And of course, what we'd like to do is to understand which of these scenarios is actually realized in interesting theories like QCD4 and QCD3. And I described how one would distinguish these if one knew how to simulate these theories in the larger limit as we approach the end of the conformal window. But unfortunately, we don't have any ideas for how to do that analytically. In some sense, the best thing that we can do analytically is to analyze things in this weakly coupled regime. And then in that regime, we can have some weak indications for which scenario actually takes place. So for instance, if at weak coupling we see that a dimension of some operator goes down, then that would give some weak indication in favor of the merger scenario. If we see that the coefficient of the effective potential goes down, that would give a weak indication of the CFT instability scenario. And similarly, for the other scenarios, we can find some weak indications of them in the weak coupling region, but we don't have anything more than that. In the special case of QCD3, there is some, so in that case, as I mentioned, we have this 2-dimensional conformal window parameterized by x over n and by an f over n. And in that case, in some regime of the parameter space where we're in the planar limit, we can show that neither of the CFT-related scenarios can happen, because in this case, we control the infrared fixed points very well in the planar limit, and we know that they do not merge, and also they do not become unstable. But we still can show that there is a transition in this case. So in this case, this transition cannot be governed by a merger or an instability, and we must have one of the other scenarios. But again, we still don't know which one, and that will require lattice simulations. So thank you.